Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined again by Anjali.
Hello, my name is Anjali. I'm a student in mathematical physics, and we're going to be talking about some mathematical physics stuff later
Yeah,
in this program. So,
we've got
yeah,
some quantum, we've got some logic gates, we've got some quantum logic gates. I'm really excited. We're also joined potentially by you. If you're watching live, you can join in as well. It's my square at the top, Anjali's underneath, and then down there could be you. That's slido.com/OOMC. If you're over at slido.com, you can join in over there to let us know. And that's also where we run polls. I have one that I always do, which is, how was your day today? It's a way for me to find out if I've done the live stream right. Ooh, I'm getting an error message. Maybe I'm not doing the live stream right. Let's find out. Okay, one person's having a 3-star day. That's a start, I guess. Right, okay. While they're joining Slido and letting me know how the day is, so far, not excellent. I guess I could also ask, Anjali, how's your day going? How are
I
you
think
doing?
it's good so far. So I'd say a 4.
A 4, right? Yeah, that's pretty good. The average at the moment is 4 because we've only had a few votes and they've been. Hold on, interesting problem. How do you get the average to be 4? Are there non-trivial ways to get the average to be 4, other than just having one person who says 4 and 3 people who say 3, 4, and 5? What other sets can I think of where I guess I want the sum to be exactly 4 times the number, so it's like partitioning or something? I don't know. Maths. Good times. Good times. Right. Let's see if I can make my computer less unhappy. It's a technical show. Anything could happen. Anything could happen at any moment. Chat's moderated by Lillian today. While we're doing thank yous, let's remember that we're supported by the Maths Institute. Also, Jane Street, who gave me a T-shirt. I might talk about the T-shirt if we have time. Let's find out. Joe is here. Joe has reminded me. Joe says that they were at the open day and they went around New College. So exciting. I'm at New College. Actually, did you say which college you're at for
I'm
balance?
at Wolfson College, so
Wilson
I don't
College.
think this was on the open day tour,
Of
but
course, because it doesn't have
definitely go to.
undergraduate maths
It does
students.
not
It does
have
not. Okay.
undergraduate. Yeah,
You should tell everyone it's the best college because then there's
it's
nothing
totally the best college.
there's nothing they can do with that information if they're applying for undergraduate maths. Right, okay. I mean, there's an attempt at a balance because I'm at New College. Reminded about the open day. I was at the in-person open day. Actually, was at the in-person open day, or we did this in-person open day. If you weren't there, but you would like something like an open day, we're doing one online. So on this YouTube channel, we're going to go and do some information about maths in Oxford. That's me, and then I've got some tutors and students to. I'll be in a big Zoom call, and we'll do some Q&A stuff. If you're interested in applying for something like maths at Oxford this year, to start in 2026, let's say, then we're doing a thing on Saturday that you might be interested in. That's on the Open Days bit of the website. I put a link on the screen. If you search for Maths Open Days Oxford, it should come up. And the YouTube recordings of what we're doing, they'll be live on this YouTube channel, and the recordings will be on this YouTube channel to the end of the year. An anonymous person says they were at the open day, and so was Arthur. I realise that sounds weird in that order, right? If I do, I should have done Arthur first and then the anonymous person. Okay, cool. People are having quite a nice day, so I'm going to stop the votes. And hi to Felicity as well. There you go. Felicity in chat. Also, remember to mention Maths Club, which is the show that we're currently doing. So I don't know how I keep forgetting about it. But Maths Club is a show that we do on the web. You might have heard of it. It's happening now. It comes with a website, which links to this live stream if I remember to put the link on. So you can get the link to the latest live stream, but also loads of previous episodes, including one on quantum waves, which I had Anjali on, where I tried to do too much wave theory all at the same time. I tried to do chemistry as well. It was a bit of a mad episode. But loads of other ones, not just me trying to do too much quantum stuff. Available on the Maths Club website. Each of them, almost all of them, have further reading notes as well. So if you like one of them, then there's usually a button that says further reading where you can find out more or get corrections. Right, that's enough burritos, I think. Start moderating the burritos a little bit. Right, okay. Chat's so fun. I'm going to hand over to Anjali, I think. So I start with, we're going to do quantum, but I think we said logic gates first. So a bit of computer science in a way. and I'm going to try and make my computer less cross. So I'm handing over to you.
Okay, perfect. So we're going to talk a little bit about quantum computing and more importantly, try to understand the mathematical framework behind it. And to do so, we need to first understand how information is represented and processed in any computing system. So at heart of this is a simple question, that is, how do we describe information in a way that machines can work with? So we know that classical computers are built on a framework to exactly do that. And although quantum computers behave a little differently, many of them still rely on the same um, ideas, just extended into a new regime. So we're going to start with the most fundamental unit of information, which is a bit, right? So we know in classical computing, we have 2 bits, zeros and ones. And any kind of information that we want to represent is a string of zeros and ones, right? So we have something like this, and this could possibly represent a number, an image, or anything that we see physically. But it is also important to understand that, so the output of this can be like an image or some number or text. But information fundamentally is physical, is physical. And what I mean by that is these bunch of zeros and ones are just not abstract numbers that we are pulling out of anywhere, but these are basically made out of physical systems like capacitors or transistors. They're built out of circuits. And these circuits are what we feed qubits into and get these outputs. So we try to flesh that out a little clear, in a clear way, and look at things called logic gates.
I love this idea that information is physical, by the way, that we do this sort
Yeah,
of abstract maths where it's all zeros and ones. You know, my zeros and ones aren't really physical objects, but in the
right.
real world, you've actually got to build a thing. And there's some sort of information density, I think, as a concept where the maximum amount of energy you can get in a cube is limited by laws of physics or something, because data has to take
Right.
up a size, which
Yeah,
weird to think about.
it's
Sorry,
yeah. Um, so far we have bits, so we have zeros and ones. And what do we do with these bits? So we perform operations on these bits and we do them using logic gates. What are logic gates? They are something that take in these bits as inputs and perform an operation and give you some outputs. So let's look at three basic fundamental logic gates, which are AND gate, OR, and NOT gate. So AND gate is represented by this kind of symbol. It takes in two inputs, gives you one output. Let's say the inputs are A and B, the output is C. So you take in, so A and B could be any combination of zeros and ones. So we have two digits. What combinations can you have for A and B? There could be two squared combinations, right? So we could have a 0, 0. Both the inputs could be 0. You could have 1, 0, like A be 0 and B be 1. It could be this, or both inputs could be 1. And the way AND gate works is you get 1 as the output only when both of your inputs are 1, which is like the final case here, both your inputs are 1, that is the only situation where you get the output as 1, and rest, all the situations, you get 0 as the output. And that's how AND gate is defined.
If you have more than 2 inputs, I guess you could build this out of AND gates. But if I think about the word AND, what do I say? I want A and
Yeah.
B and a third thing as well, then.
Right. Actually, with the OR gate, it kind of performs um, an addition sort of. So you could have like either A or B be 1. So you have the same kind of inputs. And when either of your inputs is 1, you get the output to be 1. And in the first case, it's 0. So in the first case, you need both A and B to be 1. In the OR gate case, you need either A or B to be 1 to get the output 1. The NOT gate is kind of interesting. It takes in 1 input and gives you 1 output. So let's say it takes an input A. It gives you an output A bar, which is essentially which is essentially the conjugate of your input. What I mean by that is if A is 0, you get a 1, and if A is 1, you get a 0. Right? So that's NOT gate. Now these are classical bits and classical gates. And these gates can be represented as matrices. So the bits can be represented as something called column vectors. Let's say I can represent the 0 bit as 1, 0. It's a vector essentially. And you have a 2-dimensional space. Let's say you have an XY axis. And a 0 bit is essentially a small tiny vector of length 1 along the x-axis. And similarly, I can represent 1 as 0, 1, and it would represent a tiny vector along the y-axis of length 1.
Okay, pause for a second, because there'll be someone at home who's worried about the fact that there's numbers on the left and vectors on the right, and also maybe equals here. We're thinking of these vectors kind of representing the binary ideas of 0 and 1 without trying to state that vectors and numbers are like secretly the same thing or something, because they're sort of 2D on one side and 1D on the other side. Well, I suppose it's an interesting idea. It's not one I've seen before, that you can have 0 and 1 as sort of things that are so different that they're pointing in different directions. Sort of. Normally when you meet 0, it means something like no direction at all, but I guess the new idea here is that you're going to have 0 as its own thing and 1 as its own thing over there, without really a...
Yeah, I think you really expressed it quite well. So 0 is just a label for a representation in a way. So you're labeling whatever this thing is. Sorry, have I zoomed in? So you're labeling this thing as 0. You could label it as whatever. You could label it as x hat, let's say, which is, a tiny vector along the x direction. So it's not really, let's say, a number 0, but it's a label 0. And this sort of becomes more important as we go towards the quantum limit. So let's talk about quantum bits, or which are for short called qubits.
Wait, hang on. Does the NOT gate... Is it true that the NOT gate just switches zeros and ones? Is that if I switch those arrows that you've drawn for the little, you're thinking of them as arrows. It's sort of new to me. So you're switching the arrows. Is that a reflection in some sort of?
Essentially, it's like a reflection. It's rotating your zero like completely to an opposite phase, or like if you have a zero coming in, you get a one coming out when you pass it through the NOT gate. If that makes sense.
Yeah, in geometry, that's a thing. I think that's just a reflection geometrically. If you start with that, Inora in chat says unit vector, which is a useful phrase. Thank you, Inora. If you start with that unit vector down there and you do an operation that returns this one pointing upwards, and at the same time, if you started with that one, you return this one. I mean, we've only got two sorts of input, but so far that looks like a reflection in the line y equals x to me. I don't know if that's relevant to information theory or quantum or whatever, but that's kind of nice. This geometric, having 0 and
Yeah.
1 in different directions give you this kind of geometric intuition
Yeah, I
of
think
what
it's a
not gates
good
are doing.
observation.
Now I want to think about the other ones, but I'm going to think about the other ones and let you carry on with. We're going to go to qubits next. So
Yes. Okay. Let's get to qubits. So I'm going to represent a qubit within these kind of brackets. These are called kets. And this notation is called Dirac notation. So the fundamental classical bits that we had, zeros and ones, will now be represented as ket 0 and ket 1. The Dirac notation, it's everywhere in quantum mechanics. It's a very useful notation. But for now, what we need to understand is anything that is written within these brackets is something quantum. So if I write a quantum state, psi, I initially had classically that the quantum state could either be 0 or 1, as we previously saw. But what happens in quantum mechanics is you can have a superposition of two states, and I'm going to explain what that means. So you could have both 0 and 1 as one state. So this is state vector. This is the quantum state vector. And these are your basis vectors.
it's a fancy notation for vectors that
Yes.
In my head I'm still thinking about these things up here. Sort of the 0, 1, 0 and 0, 1 in a stack thing. But I think Dirac, you said, invented this notation where you have, they're not even matched brackets. I mean, there's a reason for this, but the left one is vertical and the right one is like an angle sign,
Yes.
which there's a lot to take in, isn't it? So in my head, I'm still going that this thing, that 0 is a new, fancier label for the same thing you had before. It's 1, 0.
Yes.
And this 1 down here is a new, fancy label for this vector, this kind of state of having something that is on.
Yeah, so the kets are there, but like the fundamental idea still remains the same. That initially, if I had like an XY 2D plane, and I had say this was the first bit, and this was the second bit, and I could have either of these. What we are saying that in the quantum case, you could possibly have something that is a combination of these two. So you could have something like this, let's say, or what I really mean by that is let's look at a vector like this. The green vector, let's call it V. The green vector can be written as, let's say, if I go 2 steps to the left towards the x direction, let's call this fundamental unit as x hat. Let's say x hat is 1
Can we call
centimeter.
it? Sorry, can we call it 0 ket or one of the things we've already got? Sorry.
Right. Okay.
Um,
We can call it 0.
Happy. Yeah, one of the. Yeah, okay. That one was the 0 one.
Yeah. So I can write this as if I move 2 steps in the 0 direction. So 2 get 0. And let's say if I move 2 steps in the y direction, plus 2, 1, I get this new vector v, right? So this is not to scale, of course, but you get the idea that you can represent any vector in the two-dimensional space as a combination of uh, these basis vectors.
Are we
So,
quite relaxed about order of addition? It doesn't.
yeah, so
Adding
you can
two
write,
along the x-axis for regular vectors. If I add 2 along the x-axis and then 2 upwards, I get to the same place as if I went up first and then across.
right.
Okay,
So
that's
you
fine.
could
Okay.
say, so in general, you could write psi, which is the quantum state vector, as some alpha times 0 plus beta times 1, right? And these alpha and beta, these are essentially coefficients like 2, 1, any number. But in the quantum limit, these numbers are complex numbers. Alpha and beta,
Question.
and they're called probability amplitudes.
Oh, I was doing so well at visualizing these components to say that the components of this vector. Every time someone says quantum superposition, every time someone says quantum superposition, I'm going to think, yeah, adding together vectors. Because I don't know
Right.
really about superposition, but I do know about adding vectors. People in chat know about adding vectors as well. And now, rats, the coefficients are complex numbers. And that's so annoying
Yes.
because imagining a pair of complex numbers is much harder than imagining a pair of real numbers.
Yes, because complex numbers in essence are imaginary numbers, as in they contain a factor of iota, which is square root of -1. So any complex number, let's call it C, can be written as a real number A plus I times B, where A is the real part and B is the imaginary part.
If you're meeting complex numbers for the first time today, hello. We're doing it in quite an applied way, but the idea -1 doesn't have a square root, but if it did, whoa, you could use that in your number system, and you'd get a whole extra dimension of numbers out of that. Which is why I'm worried about imagining it, right? Because normal numbers I have on a line, complex numbers kind of two-dimensional. They have this dimension A and this other degree of freedom. What multiple of I would you like? And then I suppose you might think that they have a component of I squared, but oh no, I squared is just -1, so that's just back to being real again. So this is
Right.
as
I
much
think
mess as you get.
complex numbers in themselves are like a whole, it's like a whole new world to be discussed about. But what is relevant to us right now is just the fact that these complex numbers represent probability amplitudes. And what I mean by that is alpha squared, and we write it as mod alpha squared, because when you have complex numbers, squaring them gets a little different than we normally square it. So every complex number has a complex conjugate, which is written as C star. So this is the complex number C. And this is the complex conjugate C star, which is where you essentially replace I with a minus I. So A plus IB becomes A minus IB. And C star is the complex conjugate of C. So anytime you have something with a star, it just means I goes to minus I.
Sure.
And
You're trying to define. I see. You're trying to define the square of the modular. Okay.
yes,
Sorry. Yeah. Carry on. Okay. Oh, I like
so
this. This is good. Okay. Go.
so when we say mod squared, where alpha is a complex number, it means you're multiplying alpha with alpha star. So you're essentially doing so let's say alpha is C here. So you have a complex number A plus IB multiplying with its conjugate A minus IB. Can I have someone in the comments tell me what the square looks like?
Okay, chat. We've got to do first inside, outside, last, multiplying out some brackets, and we've got to remember that I is it's just the letter in there most of the time. Except if you see I squared, that's the
Yes.
number -1.
So definition
The
of
only rule.
I is square root of 1. So I squared is -1.
I prefer. This is a hot take, perhaps. While chat is typing, I
Okay.
prefer to define to not say any square roots and to define I squared. So I is just this thing. Just this thing. It turns up as an extra dimension, and there's an extra rule that I squared is -1. And if you see an I squared, you get -1, and that way you don't have to say square root at all, which is good because actually explaining square roots is surprisingly subtle. People doing A levels or equivalent will maybe already have met some sort of argument around what is the square root of 9. Like really, what do you mean when you say square root of 9? Because once you've met negative numbers, it all gets a bit tricky. Yeah, magnitude squared, brilliant. Okay. So Enora in chat and Felicity says difference of two squares. Great spot. That is the difference of two squares.
Yes.
Yes, and
So
then the I squared becomes a -1, and it's very nice. So Enora and Felicity and Anonymous, but I feel like they might have been doing some backspacing and then pressed send. A squared plus b squared. There's a minus in there somewhere. We've seen a squared plus b squared before, I think.
Okay. That's a square of these coefficients, right? So you have as many coefficients for the qubit as many basis vectors you have. So we are looking at the case of 2 bits here, so zeros and ones. So you have two coefficients, alpha and beta. And alpha and beta are probability amplitudes, which means, so if alpha and beta are probability amplitudes, what this means is mod alpha squared and mod beta squared represent probability of finding the state psi in that particular base state. So psi was a linear combination of 0 and 1. But when you measure the state psi, finally, like you perform the operation through your logic gate and you get an output, and when you measure that output, you would either find the output to be 0 or it to be 1. And the probability with which you find the output to be, let's say, 0 is mod alpha squared. So essentially, you have the probability of finding your state psi in a particular base state. So mod alpha squared and mod beta squared give you the probability of doing that. And can anyone have a guess at what it means for these coefficients alpha and beta to represent probability? Does it like give us a constraint on the values that alpha and beta can have, or
So you said each of them is the probability of something. So you go out and you actually, I guess, the Schrodinger's cat thing is something like you have a cat, and you're not sure if it's alive or dead. So you look in the box, and the quantum universe says that that's a probabilistic thing, that you have probabilities, which they're not quite alpha and beta. You're telling me that they're the modulus squared of alpha and beta, but one is the probability that you see this thing is 0 when you open the box, and one is the probability you see it's 1 when you open the box. So yeah, okay, we need to back up a little bit. I think they do need to be between 0 and 1 inclusive, because they're probabilities, these things. And more than that, anonymous person says that they should sum to 1. That the probability thing here is that either the cat is dead or alive. I don't really know, but yes, so they're between 0 and 1, and then well, I suppose we're talking about the sum squared, right? So these are complex numbers, they're not between 1 and 1. Okay, we're going to back up just a tiny bit. I've got a diagram for this. Can I do a diagram?
Sure.
Okay, this is quite good news. I don't claim to understand the probability stuff or what's going on with quantum. Why is it all probability based? But it's good news for me following along, because before I was imagining this to be 2D, and it's not really 2D. I've just found out because there's complex numbers involved, so these are quite high dimensional things. But I have some geometry for if I'm using vectors like this, alpha and a beta, sorry, that's tiny, isn't it? Alpha and beta for my components, then the news that alpha squared plus beta squared should be 1 in some sense. Okay, if they're both real, I know what that means, right? And you do too. If these are real numbers for the x component and the y component, and the sum of their squares is 1, that tells me something about where we are in that picture. For example, this vector, they always start at the origin, by the way, to answer a question from Felicity. This vector, 1, 0, that's an example where it's got an x component and a y component, and the sum of those components squared is 1, because it's 1 and 0. You square them, you add them, you get 1. And that's also true for, this gives the game away a little bit, but 0.8, 0.6.
Mm-hmm.
So 0.8, 0.6. So that's another example of a point where, sorry, my handwriting's really bad today. I'm really small. Sorry about that. 0.8, 0.6 is another example. Okay, they're both still real numbers. I haven't engaged with the complex numbers part of what you're saying at all. But that's another example where the squares of these numbers add up to 1. I can't use them as probabilities because they add up to 1.4. They add up to 1.4, it's too much. But the sum of the squares adds up to 1. And actually, I know something about all of the pairs of these. Anonymous has got it in chat as well, that if you want the squares of these things to add up to 1, that's a circle. So I do have this nice kind of geometric thing that I can have in mind now, which, okay, fine, these things can actually, they've got an extra degree of freedom, because each of them, because they've got this kind of complex phase thing going on. I like to think of my complex numbers as having a magnitude and an argument. If people in chat have seen this before, then they'll have seen this r e to the I theta thing for modulus and argument. If not, don't worry about it. There's some modulus that Angelique's told you defined up here, a squared plus b squared, that I care about because it means something to do with probability, and some more complexity that I don't care about so much. So I can have this circle in mind to say, okay, if you're over here on the circle, if the real quantum state is over here and you look in the box, then it's definitely going to be 1. If the real quantum state is over here, then when you open the box, it's a combination. Maybe you see 1, maybe you see 0, state 0, and maybe you see state 1, because it's got a bit of component in each of them. And the rule is something like 64% of the time you see state 0 and 36% of the time you see state 1, because I square those numbers. And their probabilities, they're supposed to add up to 1, which is why I'm on the circle. So in my head now, it's kind of a circle. The closer you are to the x-axis, the more likely you are, there's probabilities in here, the more likely you are to see it in that state. And the closer you are to the y-axis, the more likely you are to see it come out as the y-axis. Which is this weird idea that before you open the box, the cat might be in there with its state describing what's going on. That state could be spinning around this spinning around this thing. I don't know what the physics are. We'll probably get there, but it could be spinning around and changing over time, so that depending on when you open the box, you might catch it at a moment where it's very likely to be alive, or you might catch it at a moment where it's not. Um, it might be very likely to be in state 1 or 0. If, unbeknownst to me, inside the box, this thing is whizzing around the circle, then I can open it at the right moment and get the state 1, which is maybe the one I want. So it's weird. Okay, so I'm imagining the thing on a unit circle somewhere, and the components square to give probabilities. And secretly they're complex numbers, but okay.
And yeah, that makes perfect sense, because the system has to be in one of the states at the end, right? So at the end, the probability is square up to 1, and that just means the length of your vector is always 1, and you can sort of rotate it around the plane, like the two-dimensional plane, and that's the basic idea. What do you do with these bits now? What do we do with the qubits? So we had 0 and 1. We initially had classical gates, which transformed your bits into different kinds of outputs. So we look at quantum gates. And these, again, are basically transformations on your qubits. So you have a qubit, let's say 0. You perform some transformation to it, and you get some kind of output. And these transformations, they are represented by matrices. So we saw these can be represented by column vectors. So we had like 1, 0. So the transformations are represented by sort of matrices, let's say A, B, C, D. We have a qubit thing, so it's a 2 cross 2 matrix. And these matrices act on your qubits. So let's look at an example of a quantum gate. We look at something called the Pauli X gate.
I wonder if it's going to be my reflection one. I've had time to work out what reflection is in terms of matrix linear transformation. It might not be, though. Let's find out.
Do you want to share it right now?
Well, so a reflection would be, I don't know, maybe only let me do this if it's relevant. If it's not relevant, don't let me do this. I'll put it in further reading.
Okay.
But it's got some ones and minus ones in. I think it's got zeros on the diagonal and minus ones off the diagonal. I've seen at some point in A level, I saw an equation for a reflection matrix to sort of flip things. I guess it's, sorry, not minus ones. Reflection, not
Actually,
rotation.
we're just going to look at that.
Is that what we're going to do? Oh, okay, brilliant. Okay, carry on. Yeah.
So the Pauli X gate, it turns out to be, rather than just me giving the matrix, it turns out that it's like a quantum counterpart of the classical NOT gate that we saw earlier. So the reflection one that you're talking about, when you have an input 0, you get an output 1, and when you have an input 1, you get an output 0. Yes. And this matrix is essentially your matrix for the...
That's my reflection matrix, right? No, I don't know if people have seen matrix transformations, right? But if you have to know about matrix multiplication for this bit, sorry. But if you're going to do that, okay. So if you throw in a vector, then it reflects in the line y equals x. The vector you get out is the mirror image.
So let's say we are throwing in the 0 bit into this box, into this transformation, and we want to see what we get out of this transformation. So how we write this is you have the matrix so this is X, which is the Pauli X gate, same as the classical NOT gate. And you act this on the state 0. So state 0 is just 1, 0. And there are only special kind of matrices that you can multiply. It turns out, so every matrix every matrix has a certain number of rows and a certain number of columns. And so we have, for this matrix, you have 2 rows and 2 columns. So it's a 2 x 2 matrix. We write rows into columns. And here you have 2 rows and 1 column. And you can only multiply 2 matrices when these 2 indices match. So the number of rows in both the matrices should match each other, which is what is the case now. And the matrix that you get when you multiply the matrix, it matches the outer dimensions. So thing you should get finally should be a 2 x 1 thing. And how you multiply this is you take the first element over here from a matrix, you multiply it with the first element in the column vector. So you have a 0 times 1 plus you have this multiplied with this, so a 1 times 0. And then for the second row, you multiply the first element of the second row, so 1. So this multiplied with this, so 1 times 1 plus 0 times 0. So this is essentially 0, 1. And if you remember the qubit representation, this is exactly the bit 1. So,
Sorry.
exclamation mark. So we had x acting on 0, which gave us 1. And that's exactly what the NOT gate does, right? So you have one kind of input, you get the other kind of output.
Okay, so I can think of that matrix as being a kind of classical, it does the right thing for my NOT gate, it reflects. If you're under the rules of matrix multiplication 5, if you give it 1, 0, you get out 0, 1, and if you give it 0, 1, you get out 1, 0. It does the reverse to the other one as well. But I guess it does things on these complicated states as well. So the ones with alpha and beta in as well, it'll do something. I mean, because it'll switch the zeros and ones in those, which is a bit like switching the alpha and beta.
Yes.
Forward, so
we have another quantum gate called the Pauli Z gate. And this actually does not have a classical counterpart. Classical counterpart.
I was trying so hard to understand things in terms of classical counterparts. Okay.
Yes, but let's look at the matrix and see what it does to the inputs. I think that will help us understand it better. So Z is given as 1, 0, 0, minus 1. And let's see what it does to let's say 0. And 0. It's Z.
So this is where I feel like the Dirac notation is not that helpful, because you write it out, but then in order to do the sum, you have to remember that the fancy brackets just means 1, 0, and then I'm being cheeky, so that you then remember it's just a vector, and then you go and do the vector.
But yeah, any answers to this?
I think if you know about matrix multiplication, then it's quite straightforward, and if you don't, then it's essentially impossible. So if chat wants to tell us... and let's do a different thing. Chat, if you know about matrix multiplication, maybe you could do a different question, which is, what does this one mean geometrically? What does this do to the vectors? I think I'll let Andrew do the kind of calculation stuff, right? Of what these numbers are. Maybe chat can guess. So it's a matrix of 1 minus 1 on the diagonal. And we're interpreting that as things it does to the x-axis. We're working out what it does to the x-axis at the moment.
Yeah, so you essentially get just 1 and 0 if you multiply it out explicitly, which is your initial 0 vector. So we see that if you give 0 to Z, it does nothing to it. it just gives you 0 back. Let's
Okay.
see what it does to 1.
Okay.
What is acting on 1? So you have, sorry, the 1, 0, 0, minus 1,
Yeah.
acting on 0, 1. So again, multiply the matrices. So 1 times 0 plus 0 times 1, which is a 0. And here you would have a 0 times 0 and a minus 1 times 1. So you would get a 0 minus 1,
Yeah. So,
which is neither of the basis states. In fact, if you factor out the minus 1, then you can write it as this, which is minus 1 times the state 1. So Z acting on 1 gave me minus 1 times 1.
Aaron,
And Z,
and Anonymous, but first Felicity, have told me that that's reflection in the x-axis, which is what I agree. There's another sort of reflection, which is confusing, and I'll think about it. But another sort of reflection, we've seen reflection in a 45-degree angle, kind of one, and this is a reflection in the x-axis. But Ruben asks, what does a negative bit mean? You've got this minus 1 times 1, and classically, I don't think that is a thing.
The bit, like the fundamental basis state, it still remains 1, and the minus 1 is sort of like a phase factor. As you mentioned, geometrically, you can think of it as rotating your initial qubit with a particular phase. So in general,
Wait, slow that down. Sorry. So you explain the minus 1 in the like physical world or the classical world. You can have 0 meaning off, 1 meaning on. You can't really have minus 1 meaning anti-on.
Yes.
But you've got this interpretation in terms of probabilities, I think, to tell us.
Right.
I mean, that's not a probability, that's -1, but we're supposed to square.
Right. So you square the coefficients, you still get the sum as 1, like minus 1 squared, 0 squared. You still get 1. So the probability is conserved, meaning you still have that vector with a length 1 over here. But what you're doing, let's say initially you're feeding in a 1 and you apply a Z gate onto this vector. What it does is it rotates it. So you get that kind of like rotation and you end up with something like this. So you're still on the unit circle, but you're like on the other side of it. I see,
but that doesn't do anything to the probability because
it
doesn't do anything to the probabilities. So if I only care about the probabilities, like you open the box, and what do you see? If you were up here before, then there was 100% probability that you saw the classical 1 thing on. And if you flip down here, I guess a negative number, but the probability I've remembered you're supposed to square. So you've squared over here, right? That squaring means that it was like mod alpha squared or something. That tells me that we now have, well, -1 squared is the same thing as 1 squared, so still 100% probability of seeing. Well, so it doesn't change the probabilities. Flips. Right, so it changes the sign on one of the coefficients, but that doesn't affect any probabilities. So it's a weird transformation that doesn't affect the kind of measurement like outcome stuff
that you get. And this sort of also tells us a very interesting thing in a way that your output is depending on the kind of input that you're giving. So it's not like a general transformation. And we will sort of look at a gate later called C0 gate or the controlled NOT gate, which is a more multi-qubit version of this. So here we are just looking at 0 and 1. But if you have, let's say, 2 more of these, so you have 1 more 0 and 1 more 1, so you have multiple qubits. In that case, you can have combinations like we saw in the classical case. So you would have things like these.
Right, I've got 2 boxes, each contains a cat. I'm quite nervous about both my cats, but they could be in different states from each other, so okay, good.
Exactly. And this is quantum. So again, we write this in the Dirac notation.
Addition is commutative, but my two cats are separate, so can't swap the
Right.
cat.
Um,
Cats aren't commutative. Every cat is unique and special. Right, inside the brackets, we're keeping track of each of the. I'm still thinking of cats, which is a little bit morbid, or is it? But I think we're having these kind of two different things now, which we're calling qubits, which fine, okay. Okay.
right. So in this case, like your general state psi, let's say multi-qubit, would be a combination of these basis states. So you have 0, 1 plus 1, 0 plus 1, 1,
Okay.
alpha, beta, gamma, and delta. And again, the probability amplitudes squared add up to 1. What the control NOT gate does is now you can have inputs like these over here. I'll just write the outputs here. So if these are the outputs, it checks whether your first qubit is 0. And if your first qubit is 0, it doesn't do anything to the second qubit. So you just get a 0, 0 and a 0, 1 as an output here. But if you have 1 as your first qubit, it flips the second qubit. So you would get a 1, 1 and a 1, 0 in this case. So the first
Weird.
bit is
Okay.
sort of called the control, and the second one is called a target. But and this is and you can construct circuits out of these kind of gates. So you have X, Y, Z, CMOS gates. There is a very fundamentally quantum gate called the Hadamard gate.
Feels like a sort of transistor, I think. Transistors in classical electrics. Sorry, let you control things. Carry on, carry on. Sorry. Control wire comes in, you've got other stuff going on, it can flip whether it's on or off. I reckon I can build one of these out of transistors if I have to.
It's
Cool.
essentially,
Okay.
sorry,
Yeah, good.
it's a combination of X and Z gates that we saw earlier. And it sort of does an interesting thing. So X for us was, it was 0, 1, 1, 0.
Mm-hmm.
And Z was 1, 0, 0, minus 1. So H is 1 over square root 2. So 1 over square root 2 factor is just to make sure that when you square and add, you get a 1. So half plus half, it's 1. And we call this a normalization factor. It's really to make sure that the length or the probability remains 1. What the matrix then looks like is you add these two matrices, you essentially add every element. So 0 plus 1, 1, 1, and minus 1. And if you go back and compute what this gate does to your 0 and 1 states, you would see something interesting. So if you apply your Hadamard gate on, let's say, the 0 state, you would end up with, this is 0, you would end up with a 0 plus 1. You would end up with a combination of 0 and 1. And you would like keep the normalization outside.
Chat can maybe guess that I'm going to ask what geometric transformation this is. But yes, that's what it does to 0. It gives you some combination of 0 and 1. 0 was along the x-axis. And it gives you that combination.
Mm-hmm.
Okay.
Yeah, and this essentially helps you create something called entangled states in a way. So you're going from a single qubit state to a linear combination of two. And when you sort of do this with multiple qubits, you end up with states in which even if you measure something about one state, you directly know the outcome for what is happening to the other state. This is a very brief idea of introducing the entangled states, and we're not gonna go like deep into that idea, but just introducing you to the sort of things that these logic gates can do. And there are no like classical versions of these kind of gates, and that is what makes them very special. So
We've got
that was
about
about the different kinds of gates,
nice. We've got about
and we are
five.
almost
We've got
uh,
about 5 minutes. We've got some quantum gates. We've got some, I think, really nice ideas about quantum. The sort of framework of what you're doing is all probability based, which might be a surprise. Um, I think we were planning to try and build something out of gates. Is there a way you can do
so you're
a tiny bit of what you can build all sorts of stuff out of, and not gates in the classical world,
right.
transistors and whatever. But
So if you have some combinations of these gates, let's say you have an X gate that you apply, then um, you have different kinds of inputs, and you apply a Z gate here, you apply a Hadamard gate, get inputs, and this essentially is what helps you build these quantum circuits. And doing that physically is quite a task, especially for building a quantum computer, which is why we don't have one yet, because these are made out of systems like photons or electrons, and you need to have, let's say, electrons in a particular kind of orientation, um, and you don't need them to interact a lot with the environment, and that is sort of very difficult to realize in an experimental setting. So building quantum computers is still on the way, and the basic idea and the framework behind building a quantum computers are these logic gates and these kind of various circuits. Um, I
is this
don't
gonna?
think
Are you gonna join? Is this joining up into a circuit, or is this? Or so there's an idea. Okay, there's an idea that you can connect these and build non-trivial stuff. At which point the fact that you've got complex numbers involved becomes relevant, because changing the so the question in chat, which you might let's try and do really quickly, which is if it's only the amplitudes of these complex numbers, the modulus squared of these complex numbers, that matters for the probabilities, why do we bother with the phases at all? Why do we bother tracking the phases of these numbers?
that's a great question, I think. But the phases matter because that is what fundamentally makes things quantum. Let me give a quick example. If you want to, let's say, go from A to B, and say you have two ways of doing it. So you do it with probability P1 and P2. What probability theory says is that P1 plus P2, that is like the total, those are the total ways of doing it. But quantum theory is a slightly different kind of probability theory where you sort of look at going from A to B, but you do uh, you you have these things squared, let's say. Um, so you would end up with an interference term, P2 squared plus 2P1 P2, where this is sort of an interference term. If you sort of um, assume these probabilities to be complex, you would sort of get a non-zero interference term, and that is what um, makes it different from the classical probability theory.
Okay.
I don't know if
I think we might have to put something in further reading now. I think.
yeah,
Also, there's a request for quantum teleportation, but I think that might be it. We'll put a note in the further reading as well, because I'm not sure we're going to get to the teleportation. But the idea is something like, as I understand it, the idea is something like if you can build an entangled state where information moves from one place to another, because you can infer. Am I along the right lines?
yeah.
So that if you have these entangled things where you know that, let's say you know either it's in state 0, 1 for these two cats, or it's in state 1, 0, then you get this kind of
Mhm.
weird effect where observing one of the cats tells you about the other cat if you know that exactly one of them is alive, which is kind of weird that you can create such a state where they're entangled and they could be far apart. I think you can then build a more complicated version which acts a bit like putting a cat in a teleporter, but it combines together that sort of idea, I think. I don't know. We'll put it in the further reading.
Yeah. Yeah, I mean, you could have like a message that is sort of that you want to send across, uh, but or like a quantum state that you want to send across, and you do it via these like gates, and you can sort of have one part of it and know what the other part is basically without measuring it.
It's a multi-qubit thing then, because you have a sending and receiving ends of this.
Right.
Multi-qubit. So I have to try to find your multi-qubits here. So you had these sort of states with at least two things going on, where these two things going on could be really far apart, and then you can maybe use that to send information, or possibly cats. I'm no longer sure about the cats. You can use that to send information, teleporting information. Perhaps disappointing that we're teleporting information rather than cats, but it could be information about cats.
Yeah, that's
A strong thing to send. Aaron says, thank you for amazing and crazy intelligence and, I guess, teleportation facts. I think we're going to wrap up the live stream bit here. I'll put some things on the website. I realised just now on the website I've forgotten to put, I normally put a kind of thumbnail for the episode, so I'll add one of those at some point so we can get on the list of episodes. Anything you want to say at the end for people who want to find out a bit more about this, or for people who want to...
I would like to recommend a book which sort of does all this logic gates in a pictorial representation. It's called Quantum in Pictures.
Okay.
It's by, I think we can attach this in the further reading part. But it's a book about um, about basically describing quantum process. I don't know if you can see
Nice.
this.
It's got a very good cover. Right, good. Okay, we'll put a link in further reading. Love it when there's a book recommendation. It puts putting the reading in further reading, or pictures in this case. Right, good. Thank you very much for coming on the stream, Anjali. Thank you for people in chat and people watching on the YouTube recording. We'll be back next week for another episode of the Oxford Online Math Club. So have a nice evening, have a nice weekend, and we'll see you in 167 hours for more Oxford Online Math Club. Take care. Goodbye from both of us. Bye.
Bye everyone. Take care.